All right, welcome back to 353 and good morning. The morning has a lot of casualties today, I guess. It's like a snow day, except it's not actually snowing. All right, so 9 a.m. lectures, not the most popular. So let's get into it. Today will be more of a, kind of review-ish, kind of wrap up, see different types of scheduling, see what we can do with memory mapping now to make our lives easier. So we can explore some dynamic priority scheduling, otherwise called feedback scheduling, I believe in the textbook. And for this, we let the algorithm manage priorities. We use set time slices, measure CPU usage, kind of like the idea of the completely fair schedule and having a virtual runtime, except a lot more simplified. And in this case, well, we dynamically adjust the priority of process, so we increase the priority of processes that don't use their time slice and decrease the priority of processes that use their full time slice or that run for a long period of time. So that is our goal for this. So for this scheduling, it's easiest to pick the lowest number, means the highest priority, because it will simplify our formulas and how we readjust things. So each process gets assigned an initial priority when it starts. We'll call it P of n. And then the scheduling algorithm just picks the lowest priority number to schedule. If it yields, if it blocks, if it gives up its execution, then we pick the next lowest number. We will break ties with arrival order. And if a lower priority number becomes ready, we would immediately switch to it. So this is preemptive. Then we also record how much time our process executes for this priority interval. We'll say cend. It's like our time slice that we recompute all the priorities for. Timer interrupts still occur, so the kernel maintains control. And then at the end of the interval, we update the priority with this formula. So we just take its current priority, divide it by 2, so it decreases. And then we add C of n, which is how long it has run for in this time slice. And then we just reset the value of Cn back to 0, keep our counting going again. So if we assume all the processes have an initial priority 0, and then they are all ready to execute, arrive in order X, Y, A, B, and we'll take another little twist of this. We'll call A and B CPU-bound processes. That means if they get selected to execute, they will execute for as long as you'll give them CPU for. And then X and Y are IO-bound processes. That means they are waiting for a read system call or something like that. They get blocked. So in this case, how we're going to model it is they execute for 1 time unit, and then they get blocked for 5. So they actually can't execute for 5. They're waiting on a read system call to return or something like that. So we should schedule something else to run. So timer interrupts occur every 1 second. Time slice is 10, or the priority interval is 10. Same things, we'll recompute the priorities every 10 time units. So in this case, we should be able to answer what is the scheduling, where each box is, a timer interrupt. It's 1 time interval. So initially, they all have the same priority. So to break the tie, we would go by arrival order. So we should pick X to execute first, right? Can't really argue about that one. So X, we would execute for 1 time unit, but it is one of these IO-bound processes. So it will execute for 1 time unit and block for 5. So it's done executing with its 1 time unit, and then it's blocked for 1, 2, 3, 4, 5. So it won't come back until 6. So we have to pick something else to execute. What are we going to pick to execute next if we can't pick X? Y, right? It's the next in order. So we would pick Y. Well, it's one of these blocking processes again, so it executes for 1 time unit, and then it's blocked for 5. So now we only can pick between A and B, so we would pick A. So we would pick A for the rest of the time. So the reason for this is even though X and Y are ready like here and here, well, they don't have a higher priority than process X, so we won't, or than process A, sorry. So we won't just kick out process A because they're of the same priority. So you would just favor just keeping executing whatever you're executing. So A will execute for 8 time units until time 10, and then we get to recalculate all the priorities. So, like I said here, at time 6, X is ready, and at time 7, Y is ready, but we don't switch them because they do not have a higher priority or lower number than what is currently executing. So at time 10, we recompute the priorities. So we take their current priority, which is 0 for all of them, their initial priority, divide by 2, which is always going to be 0. And then we add basically how long they ran for in the last 10 time units. So X ran for 1, Y ran for 1, A ran for 8, and B ran for 0. So the new priorities would be 1, 1, 8, and 0. So now at time 10, when you pick something to schedule, hey, B has a higher priority or lower number than everything else, so we just pick B for the rest of the time, then recompute at 20, do it again, blah, 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 blah. So questions about that? Fun, huh? All right, so we can change it a little bit where A and B have a priority of 6, and the others have a priority of 0, so X and Y. Again, the rest of this is exactly the same. So the scheduling this time is X and Y have a higher priority than A and B, and so we would pick either X or Y to run, and to break the tie, we'd go by arrival order, so we pick X to execute first, runs for 1 time unit, gets blocked, then, like before, pick Y, runs for 1 time unit, gets blocked, and now we have no choice but go between A and B. They're both of equal priority, 6 in this case. So we just break the tie based off arrival order, so we would pick A. And the only difference now is that at time 6, when X is now ready, it has a higher priority or lower number than A, so it's going to kick it out. So it will kick it out, run for its 1 time unit, block for 5. So at time 7, Y is ready again. It has now a higher priority than A, so Y would immediately run. Then at time 8, then we only have the choice between A and B, so we go back to A again for the same reason we did before. So A executes for 2 time units, and then we recompute the priorities of everything. So in this case, the only difference here is that the initial priority of A and B were 6, so it would be 6 divided by 2. The initial priority of X and Y was 0, and then we just add how long they ran for. So X ran for 2, Y ran for 2, A ran for 6, and B ran for 0. So now if these are the newest priorities, well, X and Y still have higher priority than process B, which is the next, but process B has higher priority than process A. So right now I only have a choice between A and B because X and Y are blocked, so I'm going to pick B in this case, right? So I'll pick B in this case. It'll run for 2 time units, and then at this time X is unblocked, so X still has a higher priority or lower number than B, so it will kick it out. And then at 13, for the same reason, Y will become ready and then kick out B. And then at time 14, we only have the option between A and B again, so we will go with B. And then at time 18, X is ready again, so for the same reason, we'll kick out X. And then at time 19, Y is ready, so we will go to Y. So questions about that? Just another flavor of kind of round robin. Yeah?
So recalculating priority depends on the time slice?
So recalculating priority happens every 10. So every 10, no matter what's happening.
Right.
Yeah. Yeah, so we'd recompute it again at 20, and if we were to carry on and go on. Yeah.
And that's dependent on the priority interval.
Yeah, so the priority interval is whenever we recalculate it, it's pretty much, the time slice is kind of irrelevant because if we don't recalculate the priority and it's out of its time slice, we're going to make the same decision anyway, so it doesn't really matter. Yeah.
For scheduling the first one, is it that they all arrive before 0, but then, so you're only breaking ties with the arrival time? It's not like some of them have arrived at 0.
Yeah, we're just assuming they all arrive at 0 in this case. Yeah, we just assume they all arrive at 0. And we have to break the tie with arrival order. Yeah?
When would the time slice be significant?
The time slice will never be significant. It's just like an implementation detail. So the only thing that matters for this one is the priority interval whenever you recalculate the priorities, because only then will you make a different decision. So sometimes they have them both, but the time slice is fairly irrelevant. Recalculating the priorities is the important one. All right, any questions about that fun thing? So we're going, oh yeah.
Is there a reason it's like PN over 2?
PN over 2?
Like for recalculating priority, like it's the
Oh, is there a reason for that formula? No, no good reason for it other than it kind of does what we want. So it decreases the priority of things that have or decreases the number or gives things higher priority if they haven't run. So dividing by 2 is a nice way to do that. And if you have run, right, you get a constant added onto you. So it's just a good one easy way to demonstrate it. You could make up any heuristic you want, as long as if you haven't run, you get a lower number. If you have ran, you get a higher number. Alrighty, so we got that, whoops. All right, so let's become a wizard. So LLMs are a thing. So there is, Llama's, Meta's large language model. You can download the model, and this C++ implementation called llama.cpp is very efficient, so efficient that people were like absolutely dumbfounded on how they could actually accomplish this. So let's see if this works. Yeah, so now this says, hey, this model now only needs less than 6 gigs of RAM, so this model is like 20 gigabytes about, and then someone made that has taken this course made like a 2-line change where it only needs 6 gigs of RAM to run now, and then everyone was like, oh my God, how did you do this? You are such a wizard, please teach me. So I will teach you what they did. They basically just did a 1-line change in order to reduce the memory consumption by like 75%. So we can use mmap. So we can control our process's virtual memory with a memory map or mmap system call, and this lets you map a process's virtual address space if you want. And we now know how virtual addresses work. We translate virtual pages to physical pages. Turns out we can do different things. The initial values of the physical pages can be something else. So what this does is the pointer it returns, which is a virtual address, allows you to access a file directly if you want to. So you can map your virtual address space to a file. So what does that look like? So let's go here. So we'll learn about this a bit later, but somewhere on your computer, you have a disk that is where all of your files are stored, right? Let's assume, because for the most part this is true, that they are stored in blocks that are the size of a page. So let's say we have a file. We'll have some other metadata here, something like that. So let's say file A, its contents span 2 blocks. So it's like, hello, I don't know, this is a very large file, something with text at the end. So it spans like 2 blocks or something like that. So this is the contents of the file. So one thing mmap allows us to do is we can mmap, and this will allow us to ask for some virtual pages and ask what they are initially mapped to if we want. So we can ask for, just 2 virtual pages in our program if we want, and just use them for memory if we don't care what their initial values are. But one of the things you can do with mmap is say, well, I actually care what the initial values of the pages are, and you can make it so that it actually maps to the same content as the file. So I can access the file through memory. So I can essentially link this page with this block of the file, this page with this block of the file, and we now know that with copy on write too, mmap is lazy, so the kernel can just set up all of the PTEs and not actually get memory for you until you first use it. Then it would generate a page fault. Then it can lazily grab a page and allocate memory for it and then fix it up and then let you use your memory. So in this case, the kernel could do the same thing where, you know, it just has some page table. With 2 PTEs referring to the 2 blocks it gives you back. So what it can do is when you first access whatever is on that page, what your kernel can do is be like, oh, there's a page fault. I have to grab a page in physical memory. So I have to grab a PPN. And I could also make its initial contents equal, like copy its initial contents from that file block. So I can put in hello there. So if I only read the first page of the file, it's already in memory. I don't have to do anything like that. I don't have to do any read or write system calls. I'm free and clear. And then eventually when I go to access the next page of the file, whatever that happens to be, then the kernel can go ahead, grab a physical page, make its contents, copy the initial contents from the block of the file, and then I can access it like that, and I don't have to do any read and write system calls anymore. So this is useful not even for LLMs, but just for using a file. So if we want to read the entire contents of like, let's be meta, so if we wanted to read the entire contents of like a source file called mmap.c and we don't know how big it is, right, we would allocate a buffer, a size of a page, call read over and over and over again until it finally returns 0, and then we're done, right? But that's kind of annoying. We'd have multiple read system calls. So one thing we could do as an alternative, which is something is not really testable for this course, but you will probably, hopefully end up using, is I can do, just open that file like normal. So I get a file descriptor back. In this case, we know it would probably be file descriptor 3. Then I can allocate this, create a local variable of the struct stat. So the struct stat, there's an fstat system call that'll basically just give you information about a file through its file descriptor. So we probably need to know how big this file is. So here, I just do an fstat system call, give it the address of stat, and then it fills in a whole bunch of data of the structs. One of the useful things is its size, so I want to know how big this file is. So the mmap API is a bit large. It takes 6 arguments. The first argument is the suggested starting address. So I could pick, if I cared about what virtual address I got back, I could say, hey, please give me this virtual address back because, I don't know, I like it. Or you can use that to do all sorts of fancy things. But null just means you don't care. In this case, I don't care what virtual address I get back is. The next argument is the number of bytes to map. So it's a size underscore t. Then the third argument is protection flags. So what should I be able to do with this page? Read, write, execute. Probably looks familiar to the bits on a page table entry. So what am I allowed to do with this memory through this virtual page? Then there's flags for the mapping itself. So some ones are like shared, private, and anonymous. So shared means like if I fork, it will be mapped to the exact same thing in the child process. So that's one way to share memory. Private means that won't be the case. And it also changes a bit when it refers to a file, which we'll see. And there's anonymous. And anonymous means the mapping isn't backed by a file. By default, it's backed by a file. If I just want some memory back to play with, I just want to allocate a gigabyte, then I don't have to set a file descriptor or anything like that, which is the fifth argument. So that's the file descriptor to map. If it's anonymous, it's ignored. If it's shared or private, then that is the initial contents that it will load into memory. And then the sixth argument is the offset to start the mapping, and it must be a multiple page size. For this, we'll always just start it at 0. So how that would look is we don't care what the address is. The length is the size of the file, and we'll just assume we're just reading the file, so we're read only. Then the flags, we'll just say it's private. Give it the FD, so the FD we got back from the open system call, and the offset is 0. So how it works is if it returns an error, it returns the special value mmap or map failed, which is probably just which is -1. And then we can close our file descriptor after that because we don't need it anymore. We have set up the mapping through the file descriptor, we don't need it. And then if we want to read the whole contents of the file, we could just use it as a big array of characters now, because now it's essentially in memory. The kernel will do it lazily, but it's essentially in memory now. So for every single byte of the file, I can just print the character. And then at the end, just like with malloc, you have a free. With mmap, you have an munmap. So this is how I would unmap my data. It takes the pointer we get back and the size to unmap, and it should be 0 if it's successful. So if we run this, we easily see that we have like our cat, where we just cat the result of the file. So this is the contents of the file that I'm currently editing. But isn't this so much better than just doing read and write system calls over and over and over again? So I just mmap it, boom, I'm done. I don't have to do anything. If I don't even use that file, it won't even load it from the disk. It will be nice and lazy. So, cool, huh? All right, what about if I wanted to modify that file? Well, we can see different ways to get seg faults now, even though we know seg faults aren't a thing. So I have it as read only. So let's say I tried to change the contents to all, I don't know, it's 9 a.m. Let's say I wanted to change the contents file to all 9s. If I do that and run it, any guesses what will happen? It dies? Probably, right? So I run it. It says terminated by seg fault, address boundary error, which is kind of a bad message. What that actually means is, hey, we're trying to write to it, and this write flag is off. So it's read only, so it should say like read only page or something like that. But for some reason, it gives us a very unhelpful message, which is that. If we wanted to try and change the contents of the file, we could try to do like, hey, let's add this prot write flag on so that I can actually change it. So if I do that and run it, I might nuke my file, right? Fill it full of 9s. So let's run it and see. So I run it. I see the contents of the file again because I'm printing it before I'm changing anything. But I'm looking at the file right now. It doesn't seem to have changed. Maybe my editor just has it buffered or something so I can look at it. Nope, contents of the file is still the same. So the reason for that is reading or updating it is kind of a pain. I'm probably gonna have to change more than one thing. So private means this mapping is only valid for this process, and it's not going to actually change the contents of the file if you write to it. So everything just stays in virtual memory. But if I do shared, if I can type shared, whoa. So if I do shared, who cares about validating? So if I do shared, well, it should actually reflect in the file. Probably won't, but let's see. So I run my program again. No, I get another address boundary error. And this one's even more of a pain in the butt. So the reason this is because you need to be able, if you want to change the contents of the file, you must be able to update the virtual memory. So that was with that prot. Oh, wait, did I delete the prot read? Oh, whoops. That's probably why it got deleted. So I have to add prot write in. I'll probably still get an error. Yeah, so I get an error, but I get another error where now it says, good thing I wrote asserts, right? So now it says assertion, this mmap or data does not equal map failed, so mmap returned an error. And then it aborted and all that fun stuff. So I could print off, in this case, let's say p error, mmap, let's see what we got. See how helpful this is. Just says permission denied. Isn't that helpful? What that means is, well, your protection flags need to measure or match, if it's backed by a file, what the flags are on the file. So for this file, it has read only, so I'm not allowed to write to it. So if I want to do both, I have to change this to be, what is it, read write. So I have to have the file descriptor open for reading and writing. So now, if I finally do this and run it, it doesn't really complain at me. It runs, and I'm changing the whole contents of everything to 9s. My editor didn't change, but it's probably buffered, because if I cat the file, I can see that it's now full of 9s. So that's one way you can update it. You don't have to do read and write system calls if you want, if they're backed by files. mmap is totally the easier way to do this. I guess, and you can tell VS Studio, there we go. So now I open it, I change the file, it's all full of 9s. I'm not getting it back unless, I use git properly and just, git restore. Yay, ow. Oops. So good thing I used git even though I did something stupid. So that was our mmap example. So any questions about that? Probably a good way. Most of your, if you look at the source code of your compilers for whatever reason, they're just going to mmap your source code, and that's how they give you easy messages and stuff. They just refer back to the contents of the file, which are already in memory, which is nice and efficient. So that is to say, mmap is lazy, just to say it again. Sets up the page tables, doesn't actually read from that file. Basically, it just creates an invalid page table entry during the mmap call that says that the kernel uses the remaining bits for bookkeeping information. So what should I do to actually get initialized memory for this page table entry if the user tries to access it, so I can go ahead and fix it up. So the first access, that generates a page fault. And like what we did with copy on write, where we handled the page fault by copying a page, this time the kernel would handle the page fault by actually getting a page and then copying that data from disk and reading it in there. And this also ensures that only used parts of the file get read. So I can just mmap a giant file, and I only pay for what I use. So back to the question, how can I actually just, use a 20 gigabyte model and only use 6.8 gigs of real memory? So turns out everyone was really confused because they were like, hey, to load the model into memory, that is 20 gigabytes, I have to read a 20 gigabyte file. But turns out when you do model inference, so when you use the model, it's sparse, so you don't use all of it. So you don't actually need to use all the data you have written in. So what they could do instead, which is what they did, tablet. Yeah, which is what they did instead is they just nmapped that whole file, and then that was it. So they changed all the read and write calls, they just got rid of them, and they just nmapped it. Yeah?
So in the example where you write to a file, are we writing directly to disk, or are we writing to this?
Yeah, so the question is, when I'm writing to the file, am I writing directly to disk, or when is that happening? And the answer to that is, for the most part, the kernel will be lazy and not write it to disk until it absolutely has to.
Okay, so we are writing to the virtual pages first?
Yeah.
And then
Yeah, so you're just writing it to memory first, and then it might not be synchronized to disk. And we'll get into that a bit more once we talk about disk towards the end of the course, too. But basically, yeah, writing to disk is slow, so it'll get avoided at all costs. So in this case, we should be able to figure out a few things. If I just mmap a 20 gigabyte file, well, that's going to set up a whole bunch of page table entries. It's not going to actually do anything. So one question we should be able to answer is like, hey, well, one, how much So how much space or how many page table entries, or well, what's the total amount of space we need to just set up just the page table entries for a 20 gigabyte file? So we could probably do this math. 20 gigabytes, that's 2 to the power of 30. So I'll just keep it in powers of 2 for now. So the total number of pages I need for this would be like 20 times 2 to the 30 divided by my page size, right? My page size, unless someone tells you different, is probably 4096 or 2 to the 12. So that means I need a total of, what, 20 times 2 to the 18 pages. So how many page table entries would I need?
The lowest level you need 20 times 2 to the 18. Then you need each of them.
Just page table entries just for that in total. Trick question, right? It's the same. I need 1 entry for each page. It's the same number. So in this case, yeah, that's also equal to the number of PTEs I need. So the total space I need is like 20 times, whoops, that should be 2, not 20, yikes. So 20 times 2 to the 18, so that's the number of page table entries we need. And if I need the total space just for page table entries, that would be times the size of a PTE, which is 8 bytes on our system. So that would mean I need essentially 20 times 2 to the 21. Or if I change all the bases, 2 to the 20 and then just take a 2 out and multiply it, that's the same as 40 times 2 to the 20, which is the same as 40 megabytes. So I need 40 megabytes just to set up the page table entries for this 20 gigabyte file, right? And those would be spanned across all of our L0s, right? We're not arguing about how many L0s we need yet or anything like that, but everyone get that number. All right, so someone said plain stop that, you know, just the space to set up the page tables for this is 40 megabytes. Is that true? Or would we need some more information to, or would we need more pages to actually be able to use this information? Yeah.
It's not just the L0, and then you have to get like L1, L2.
Yeah, this is just the all the entries across all L0s. So if we wanted to be pedantic about it and figure out how much space we actually need in the best case scenario to set up page tables, well, what do we need to do? So we have 2 to the 20, or sorry, 20 times 2 to the 18 pages, right? And we can figure out how many L0 page tables we need that are completely full. So we can fit 2 to the 9 entries in a single L0 page table, right? So that means in the best case scenario, we have 20 times 2 to the 9 full L0 page tables, which is another way just to say, was it 10,000? I think that's the number. Is that the number? Yeah, so that's the number. So I need this many full L0 page tables. Everyone see how I got that? All right, so best case scenario, how many L0 page, or sorry, L1 page tables do I need in the best case? Yeah.
So you divide by 512 L1 page table entries,
So take this number and divide by 512 again. So that means I have 20 full, that's L1 page tables. Right, which would mean 20 pages worth of memory. Do I need a new L2 page table? Sorry? Do I need one? But I assume my process is already running, right? So my process is running, it already has a L2 page table, so it doesn't get a new one. So this is it. So in total, that 40 megabytes was like this number times the size of a page, right? That gave me my 40 megabytes. But that is not the true answer. If we want to be turbo nerds, in the best case scenario, we actually need another 20 pages for the L1 page tables. So in total, we actually need 10,240 plus 20, which is 10,260 pages for all new page tables, which, I mean, if we do the math on that to get that size, so it's that number times the size of a page, right? So if we take that number times the size of a page and then figure out the megabytes, what we actually get is 40.0781 megabytes. So wasn't that worth it to do all that extra thinking just to get another 0.7 and be technically correct? So now you can go back to that form because in the discussion they're like, yeah, it takes another 40. You could say, no, it's at best case 40.07. And you can waste a lot of your time just to be closer. But first approximation, just use the number of page table entries we need because it's probably good enough. But that's also the best case. And it also turns out that, well, most of the time you'll have the best case because you get back just one big contiguous block of virtual memory, and the way all the indexes are set up is they'll all be in a row. Worst case is just going to be, so this is our best. So our best case is we have our L2 page table, and it kind of makes sense because the rest of the address space is like, if we divided it up between our L1, L0, and our offset, the total number of space here is like 30 bits, which to the 30, if we did that, if we were addressing bytes at a time, that's 1 gigabyte. So if this is a 20 gigabyte file, makes sense that we would have 20 full L1 page tables because, well, that's everything, like basically at best, each entry in the L2 page table can map 1 gigabyte of memory. Kind of makes sense if we use everything there. That could map 1 gigabyte of memory. So in the best case scenario, we have 20 that go to a whole bunch of full L1 page tables that are full, that have 512 each, and each of those L1s have 512. So worst case we have is if we straddle some boundary where all of our L0 entries must be contiguous. Worst case is, well, we still have an L2, but we might use 21. And we might use 21 in such a way that in this first actually it might be 22. In this first L1 page table, right, it could only have a single entry pointing to an L1 with a single entry. And then all the rest of them would have to be contiguous. So for all of the rest of them, these would all be full, like our 20 before. And then they would all point to full blocks. And it would just be the case where in the last L0 here, this one has 511 entries instead of 512. So we're just straddling that boundary. But worst case, it just adds, what, an extra 2 pages. So it adds an extra page from L1 and an extra page from L0, but it doesn't make much of a difference. Yeah?
Well, you have a chain of like 4 page tables. I thought that goes from L2 to L1 to L0.
A chain of 4.
It seems like you drew from L2 to L1.
Oh,
To L0.
there. Does that eliminate my chain of 4? Sorry, like that. Sorry, yeah, this row is all L1s. I got too excited with drawing a whole bunch of lines. But yeah, there's only 3 levels, and we only ever have 1 L2. Whew. All right, questions about that? So we went on a whole adventure just to get that stupid number. Again, I don't know. I'm weird. I read posts, and then I'm like, that's not technically correct, and then I figure it out, and then I don't know. That's probably how I ended up here and why I'm now in university forever. So, any other questions before we wrap up our fun morning lectures? Everyone loves morning lectures. All right, so with that,